Hi everyone. Today we are going to be talking about isotopes and ions. So first and foremost, let's do a warm up from everything that we talked about our previous class. So if you can just pause this video and answer these questions. All right, I hope you paused it. I'm going to show the answers on the next slide. We had oxygen, right? And the atomic number of oxygen is 8. So that means that we have 8 protons. And then the mass number was just about 16 or 15.999. So we can round that up to 16. We know the number of neutrons is going to be the mass number minus the number of protons. So 16 minus 8 is 8 neutrons. And then the last answer you might not have known yet, because that's actually what we're going to talk about today. But the reason that oxygen's mass number is not exactly 16 is because we have different isotopes of oxygen. Isotopes are just different atoms of the same element that actually have a different number of neutrons. So like I said, we're going to talk about that today. Now, Rutherford did the gold foil experiment, and he made 2 discoveries with that. Number one, he discovered that the atom is mostly empty space because a lot of those alpha particles went straight through the gold atoms. And then the other discovery he made was that there's a hard positive center to the atom, which he called the nucleus. And remember, he discovered that because some of those alpha particles were hitting that hard positive center and being deflected at angles or even straight back. And he know that alpha particles were positive, and we know that like charges repel. So that positive charged alpha particle was repelled by the positively charged nucleus. And then last but not least, we had Bohr's model versus Schrodinger's quantum model. And Bohr's model had those electrons orbiting the nucleus in set paths, whereas the quantum model has the electrons in a cloud of probability around the nucleus. So that's the difference between those two models. All right, so I mentioned this already, but let's talk about isotopes. So isotopes have the same number of protons, so that means it's the same element. However, they have different numbers of neutrons. So because they have different numbers of neutrons, those atoms actually have different mass numbers. So even though they're the same element, because again, they have the same number of protons, they have the same atomic number, they do have different mass numbers. And that's why our mass numbers on the periodic table are not perfectly, round numbers, because those mass numbers are actually weighted averages of all of the masses of the different isotopes of each element. So here's the 3 isotopes of hydrogen. You can see that one of them, protium, has only 1 proton. And then we have one with 1 proton and 1 neutron, and then 1 proton and 2 neutrons. If we look at hydrogen on the periodic table, we can see that the mass number is 1.008. So the most common isotope of hydrogen is just the one with 1 proton, this protium. But there is a little bit of these 2 isotopes of hydrogen as well. Let's look at the 3 isotopes of carbon. So we can see that we have carbon-12, carbon-13, and carbon-14. The highest percentage of carbon in the world is carbon-12. And we know that the atomic number of carbon is 6. So that means we have 6 protons and 6 neutrons. This is one of the types of isotope notation that you'll see. Let me do it with this rectangle. This is one of those types of isotope notations that you'll see when you see the actual name of the element and then the dash and then the mass number. So this is one of the ways that you can kind of talk about or write down, identify a specific isotope of that element, because what it's telling you is, okay, this is carbon, which is the atomic number 6. So there's already 6 protons, but I'm telling you that there's a mass number of 12. So there's 6 neutrons as well. And then, of course, we have carbon-13 and carbon-14. We can see that since carbon-12 is such a high percentage, if we look at the periodic table where carbon is, let me clear this back. The actual mass number of carbon, again, the weighted average of all of the isotopes is 12.001. So we can see that it's closest to 12 because that carbon-12 is the one that's the most abundant in the world. All right, let's clear that rectangle. So this is another way to write an isotope symbol, Again, that carbon-12 or carbon-13, that's one isotope notation that you can use. This is another isotope notation that we can use, the isotope symbol. So this big symbol right here, of course, is going to be the element symbol. And then the top number right here will be the mass number, and then the bottom number will be the atomic number. So if we look at some examples here, I can see that I have the 3 isotopes of lithium. Again, that big symbol is going to be our actual element symbol, so Li for lithium. This top number is the mass number, and then the bottom number is the atomic number. Now we know that since these are all isotopes of lithium, that means that they have to have the same atomic number, right? Because that is what signifies that this is lithium. Lithium always has 3 protons. However, these have different numbers of neutrons. So I want you to look at these 2 numbers on each of these and tell yourself how many neutrons each of them has. If you said that this one has 3 neutrons, this one has 4 neutrons, and then this one has 5 neutrons, you are correct. You could also, count them down here, but of course we just do mass number minus atomic number. So 6 minus 3, 7 minus 3, and 8 minus 3. Let's do the same thing with uranium-235. So again, if I asked you, okay, this is the isotope symbol, what is the element, what is the mass number, what is the atomic number, and what is the number of neutrons, you would say, okay, well, it's uranium. The mass number is 235. The number of protons, or the atomic number, is 92. And then in order to find the number of neutrons, we of course would take the mass number and then subtract the number of protons, or the atomic number, from that mass number. So we end up getting that the number of neutrons is 143, because 235 minus 92 is 143. Now let's talk about these masses, because I've been using these, just almost, not round numbers for the most part, but they're manageable numbers, right? And I've talked about that AMU unit, that stands for atomic mass unit. Now what this unit is defined as is 1/12 of the mass of a carbon-12 atom. So carbon-12 is kind of like the gold standard when we're talking about masses. That's kind of what we used to determine what an AMU is. And so if something like helium-4 has a mass of about 4.0026 AMU, that's about a third of the mass of a carbon-12 atom. Nickel-60 has the mass of about 5 times the mass of a carbon-12 atom. So this is just kind of the standard that we use. It makes the math easier for us, because if you see at the bottom here, that 1 AMU, if I actually put that in terms of grams, which is something that we use for mass in chemistry, it's 1.66 times 10 to the negative 24th grams. This is such a small number down here that it would just make calculations very ugly. So instead we use this AMU, and this is our what we call a conversion factor between AMU and grams. So that's what an AMU is. Again, we can just use AMU. Really, we're just looking at kind of the ratio and comparing the different elements with one another. All right, so that was isotopes. Now, again, the takeaway for isotopes is that it's the same element, right? The same atomic number, same number of protons. However, the number of neutrons is different. Now, I didn't include this in a slide. However, I do want to include in your notes just that the reason that there are different numbers of neutrons is that the nucleus wants to be stable. Right? So because all of those protons are positively charged, we know that like charges repel. So if there was no neutrons there's no like buffer, and those protons would just want to fly apart because they just want to repel one another. So that's why we have those neutrons present, in order to make those nuclei more stable. Speaking of stability, ions are actually created for stability as well. So the definition of an ion is an atom or group of atoms that have a positive or negative charge. So this happens when we either gain electrons or lose electrons. So, how are ions formed? Remember, I talked about neutral atoms yesterday, and neutral atoms happen when we have the same number of protons and neutrons. So, something like hydrogen, a neutral atom of hydrogen has one proton, and that's a positive one charge. And so, we know that that neutral atom of hydrogen would have to have one electron in order to balance out that positive charge. So, proton is positive one, electron is negative one. Positive one plus negative one is just zero. So that means the overall charge of that atom would be neutral. Now, when these things are not equal, that is when an ion is formed. So positive or negative ions form when electrons are transferred between atoms. So we can see here that a sodium atom is giving its electron to a chlorine atom. And we do this, this is called an ionic bond that's happening here, and we'll talk about that in our next unit. But because sodium lost a negative charge, right, it gave away its electron, it becomes more positive. And then because chlorine is gaining that negative charge, it's becoming negative. So we can see the Na plus for the sodium ion and then the Cl minus for the chloride ion. So why are these ions formed? I already mentioned this, but ions are formed because atoms want to be more stable. So if we look at the sodium atom right here, I can see that it has that one lone electron out there. Do we see how the next energy level down, and again, we'll talk about this more when we talk about like electron configuration and all that stuff, but we can see that the next energy level down, I have a full valence shell of 8 electrons. That is what we want, all right? We want to be stable. We want that full valence shell. So in order to do that, sodium just has to lose that one electron, and that's really easy for sodium to do. So that's why it gives it away to chlorine. Now, chlorine, on the other hand, has 1, 2, 3, 4, 5, 6, 7 valence electrons. So it just needs one more to have that, we call it a complete octet, which is the full valence shell. Again, don't worry about it too much right now because we're going to talk more about this later, but this is just why atoms would gain or lose electrons. So sodium loses an electron because it wants to get rid of that one valence electron. Chlorine gains an electron because it wants that one valence electron in order to fill its outer electron shell. So the reason they do this is because when they have that full electron shell, that full valence shell is what we talk about, what we call it, they're very, very stable. Now, positive ions are called cations. I remember this because a plus charge kind of looks like a T. So cation has T in it. So that's the positively charged ion. And metals, which are on the left-hand side of the periodic table over here. So like especially this group right here and this group right here, those ones are going to lose electrons in order to form cations. And then negative ions are called anions. And these are usually nonmetals that are going to gain one or more electrons. So again, if we look at the periodic table, our nonmetals are over here on the right side of the periodic table. And those are the ones that are going to be gaining electrons to form anions or negatively charged ions. Again, we will talk more about the periodic table later, so I wouldn't worry about it too much right now. Now, your assignment for today looks like this. If you click on this link right here, I show you how to fill in this top row of magnesium right here. But basically what I give you is I give you certain things that will help you fill in this table. So let's do the nitrogen right here. Now, I know that the isotope symbol, I have N-14, so I immediately knew that this was nitrogen. Now, if you don't know that, you can go to your periodic table and you can look at the N symbol, and I can see, again, that's nitrogen. So what I would do here is I would just write nitrogen for this element name. Element symbol, of course, we can just see from here is big N. And then the ion symbol, we don't know the charge yet, so we can't fill that in yet. However, the isotope symbol right here, I know that this 14 is a mass number, right? Because we talked about that earlier. So I know if I look at nitrogen's atomic number right here, that will give me the number of protons, which is 7. And so I can come back here, put 7 in for my atomic number, and then for my number of protons, I can also put 7. And then for the mass number, I can get 14 because it's right here on N-14. And then since I know that the number of protons is 7, the mass number is 14, I know number of neutrons will be 14 minus 7, which is 7. And also it gives me the number of electrons. So I can see that since I have 7 protons and 7 electrons, I have a neutral atom of nitrogen. So all I would put for the ion symbol is just N and then to the power of 0. So you can see that right here with this radon. Do you see how I have the superscript of 0 at the top right there? That means it's neutral. Something like this or this chlorine to the -1, that is the charge on chlorine, which I can then see that since I have a -1 charge, I should have 1 more electron than proton for chlorine. So that's what you get with those ion symbols right there. So I hope that was helpful for the isotopes, ions, and the atom practice. You have this assignment. Of course, this is for practice, and then your knowledge checkpoint is just 3 of these rows, just a random 3 of the rows. Let me know if you have any questions, and I will see you all in class.